Universal embeddings for spatio-temporal tagging of self-driving logs. Self-driving companies have accumulated massive databases of raw data logs from driving millions of miles in the real world. To leverage this data effectively, it is helpful to have tags as metadata associated with each data log. These tags have many useful applications. For example, they can be used for the rapid curation of better training datasets, efficient retrieval of scenarios for simulation, and insightful failure analysis through the visualization of the tags most correlated with the system's failures. Let's consider some potential approaches for generating these tags. The simplest option is for humans to manually tag self-driving scenes. While this approach can be effective for small datasets, it is far too expensive to scale to databases containing millions of miles. Alternatively, the outputs from the onboard perception system could be reused to heuristically reason about different scenarios based on the detections over time. Unfortunately, this approach requires extensive engineering, often returns noisy results, and cannot generalize to many scenarios that require reasoning about more than the detected actors. Motivated by these challenges, we present our approach, which takes only raw sensor data as input, yet remains a general framework to tag any attribute in a self-driving scene. We approach the problem of spatio-temporal tagging by learning a function f, which takes a data log and a tag attribute tau from a predefined set and returns spatio-temporal tag values. Tag values are tensors with both spatial and temporal dimensions and can represent any value, discrete or continuous, in the self-driving scene. For example, if we are interested in tagging vehicle density, each tag value would represent the vehicle density at a specific location and time step in the original data log. Tag values can later be pooled to generate interpretable scene tags, for example, tagging the vehicle density in front of the self-driving vehicle. Next, we provide an overview of our approach to learning F using a universal embedding to tag all attributes. Our log embedding network takes a series of voxelized LiDAR sweeps and a rasterized HD map as input. Because logs can have arbitrary length, our network is fully convolutional across time. Here we visualize the network for a single time step. Both inputs are first processed by independent backbones. Then map and LiDAR features are concatenated and passed to a convolutional header to produce a spatio-temporal embedding. Now imagine we want to tag all vehicles turning left in the scene. First, we encode the tag attribute tau, represented by a row in a learnable matrix A. Using a simple element-wise dot product, we combine the log embedding and the attribute embedding to obtain a spatio-temporal tensor of tag values V. Our approach is trained end-to-end to minimize a supervised query loss, using a variety of techniques to ensure learning is balanced across all attributes. Our model can also be extended to support compositional functions, which take tag values from multiple attributes as input and return a new tensor of tag values. Compositions enable our model to naturally handle more complex tags that relate to multiple attributes, for example, tagging vehicles turning left at a four-way intersection. We evaluate our model on a new large-scale dataset, SDVScenes, with sensor observations, HD maps, and annotations for 15 diverse scene attributes, including actor density, vehicle actions, vehicle-to-vehicle interactions, vehicle speed, and the map topology. Let's move on to some examples of qualitative scene tags produced by our model, given only the raw sensor data shown in the center and HD maps, not the actor bounding boxes shown for visualization. Vehicles in the scene, our model 21, ground truth 21.8. Pedestrians on a crosswalk, our model 1, ground truth 1. Vehicle turning left in the intersection, our model yes, ground truth yes. Maximum vehicle speed in front of the SDV, our model 10.9 meters per second, ground truth 10.9 meters per second. Four-way intersection in the scene, our model yes, ground truth yes. We also evaluate our model in the retrieval setting, returning logs with a desired tag value. For example, in the first row, we show scenes tagged with vehicle density greater than 10 around the SDV. In the second row, we show scenes where there is a vehicle tagged as turning in front of the SDV. Quantitatively, we see that our model simultaneously attains good performance across the continuous attributes of density and vehicle speed, measured by L1 error, map topology attributes measured by F1 score, and the actions and interactions also measured by F1 score. Ideally, models should also support continuous learning, in which new attributes can be added at later stages of training. We introduce 4 new attributes related to vehicle-to-vehicle interactions and show that adding these attributes to our trained model can boost performance by up to 45% compared to independently trained models for each attribute. To conclude, we introduce the task of spatio-temporal tagging of self-driving scenes and propose an approach capable of efficiently tagging a complex set of attributes from raw sensor data. Thanks for listening.